Good, whatever it is, afternoon and night. Welcome back. So we are working our way through field theory, uh, and we are specifically dealing with non-perturbative problems in field theory. So in this lecture, I am going to be focusing on one approach to non-perturbative field theory that has become extremely popular in the literature and was actually worth a Nobel Prize. And that's basically a non-perturbative approach to phase transitions. Now, first of all, let me say one thing. The material I'm going to cover is a typical statistical physics material that often gets covered by more than one course. Phase transitions are macroscopic change of the status of matter. You can think about the ferromagnetic phase transition as being a prototype of that. You have matter, you have spin that are basically disordered through the material, meaning that there's a finite correlation length in the paramagnetic phase. Maybe, for short distance, spin tend to be aligned with each other because they like to minimize the energy, but then on a certain length scale they become uncorrelated. That's the paramagnetic phase. But when you lower the material temperature, you reach a critical point, and after the critical point, you have you might enter a ferromagnetic phase in which all the spins in a macroscopic chunk of matter are aligned along the same direction. So this is a drastic change and a very mysterious phenomenon for a very long time until Landau and Ginzburg, sometimes in the middle of last century, worked out a brilliant theory to describe those phenomena and to realize that phase transitions are associated with breaking of symmetries. In this case, you clearly break the invariance under inversion of the z-axis, because this state and this state are in principle have the same energy in the absence of a magnetic field, but the system chooses one of them. The phenomenon of phase transition is often encountered in Bose-Einstein condensation, is key to understand nuclear theory and quantum chromodynamics, is basically everywhere. Even when you deal with systems that are finite dimensions, like a protein, you still tend to invoke concepts that come from the theory of phase transitions, talking about an unfolded state and a folded state and a critical temperature below which the proteins undergo a phase transition. They tend to be native. This is sort of a stretching of a concept because normally the concepts of phase transitions only apply to infinite dimensional systems, like an infinite chunk of matter, but at least to a thermodynamically large number of particles. But all this big premise is to say this is not a course on phase transitions or a statistical physics course on critical phenomena. I believe those who are interested in understanding critical phenomena should follow Potestio's course and models where these phenomena are treated extensively. Notwithstanding this, in this course we want to briefly touch on phase transitions because phase transitions are really a state of matter where you cannot rely on any perturbative approach. There's no way you can perturb a paramagnetic phase of matter and perturb it into a ferromagnetic phase of matter. They are so different. The ground state of these systems is so radically different that it's a non-perturbative phenomenon. And the way and the reason why phase transitions are non-perturbative is due to the fact that at the critical temperature, typically correlation lengths tend to diverge. So that's a typical, if you want, fingerprint of a phase transition. In the specific case of a magnet, you have you can draw a state of a diagram in which you have the magnetization and the temperature, for instance, and there's a critical temperature Tc, and as you come from, so say here you have a paramagnetic phase, meaning that you get a magnetic field only in the presence of an external magnetic field, and you have a finite correlation length of the spins, which means that here, say spin I, spin j, the correlation between these two spins is a function that decreases with the distance between the two spins in an exponential matter. And the exponent fall-off is the characteristic length scale of the exponential fall-off is the so-called correlation length. However, you reach a critical temperature, and at the critical temperature, your system can acquire two solutions. And in particular, there's one solution which contains finite magnetization, where the magnetization is defined at the average value of the spin. So this is the ordered phase of ferromagnetic ferries in this particular case. And we are interested in the physics very close to the ferromagnetic phase transition, or in general to any second-order phase transition. Second-order phase transition, for those who hasn't taken any course in phase transition, is a phase transition in which the order parameter that defines the difference between the states, for instance, the magnetization in this case, which distinguishes the paramagnetic, which is not magnetized, m equals 0, to the ferromagnetic, which is magnetized, m different to 0, doesn't vary discontinuously at the phase transition, but only the derivative varies discontinuously. Right? So you can see here the derivative is changing discontinuously. So for this order, for this reason, this is called a second-order phase transition. In contrast, you have first-order phase transitions, and typically are those where the order parameter itself is discontinuous at the phase transition. They have different phenomenology, and once again, I don't want to cover twice the same material that can be covered in another course, so I will not spend long time in the phenomenology of phase transitions. But what I want to say is that at a critical temperature, the correlation length changes from being finite to be potentially infinite in this system, because you have an ordered system. Now, since the correlation length is infinite, it means that spins of any distances influence each other. And influencing each other at all distances implies that a macroscopic amount of spins are collectively intertwined. And therefore, there is interaction all-to-all in some sense. These all-to-all interactions, even if the coupling itself is small, is of course a non-perturbative phenomenon. So this is one of the prototypical cases where you have to work out alternative to perturbation theory and field theory. And that's how we approach the problem in this course. We approach it from the field theoretic point of view of, okay, here is a good problem where we need to start thinking non-perturbative. And we want to develop methods. So we will be mostly interested in the technical aspects. And all we will need is the concept of divergence of correlation length at the critical temperature, essentially. The second observation I want to make about this is that at the critical temperature, since this is a second-order phase transition, very near to C, the magnetization is infinitesimal. It doesn't go from, say, here to all of a sudden a finite magnetization up here. You don't have, like, if this was the kind of behavior that at the critical temperature the system would jump here, then of course this would be a first-order phase transition where the order parameter itself, in this case the magnetization, would change drastically from here to here. In contrast, in the second-order phase transition, you see, the magnetization itself is a continuum function, and therefore this allows us to think that, very near to Tc, the magnetization is still arbitrarily small. So this is the stage of our problem. We want to devise field theoretic methods to describe a phenomenon like this. And it's interesting that basically these theoretic methods can arise entirely combining different tools we've spoken about in this course. The theoretical descriptions of this phenomenon that is usually referred to Landau-Ginzburg theory is not exactly the one that I will present today here. Because the point of this lecture is not so much of teaching you that theory, but rather to tell you how field theory can be used in a model perspective to rediscover that theory and reobtain the results by relying on systematic tools we have devised in this course. So we will start by constructing our Hamiltonian from renormalization group theory methods. And so the idea is to start with the Landau-Ginzburg Hamiltonian and say, okay, we already covered this reasoning, but let me do it again. We want a Hamiltonian to describe the physics near to C, and to do that, we write the most general. We use renormalization group methods, and we say we write down the most general Lagrangian compatible with the system symmetries, and we try to devise a power counting rule to order all the possible couplings we can define into the Hamiltonian in such a way to bring up something we believe is more relevant relative to others that we believe are sub-relevant. In particular, we assume there is some coupling between the spin densities, at least some finite distance, finite range coupling. So, of course, our Hamiltonian must include a term with derivative coupling, something like this. In addition, we want to include a term like this, a mass term, so to say. It's called mass term because of the analogy with the Klein-Gordon theory, but it doesn't have at all any physical meaning of a mass. But unlike in the theory that we discussed so far, this is obviously an effective parameter in this effective theory. And so it will depend on the renormalization scale. It will effectively run. And the non-renormalization scale we consider is temperature. So we think of the theory having this parameter to run with temperature. And this is also the Hamiltonian we introduced to describe the paramagnetic phase. But in addition to that, again, we introduce one other term. Now we call it U divided by 4. In the previous discussion, we were using lambda to the 4 factorial for perturbation theory reasons, because in perturbation theory, you easily generate factorial number of diagrams. Here, there's no such we will not devise any perturbative expansion, so there's no need to put that factorial down. So I will use this U0. So even U0, in principle, it changes with temperature, but we will assume that it will change with temperature in a more trivial way than R0, as I will come to see in a moment. So I don't explicitly write the temperature dependent of U0, and U0 multiplies a phi to the 4th. Now, in principle, this is of course not the most general Hamiltonian I can write, because I could have higher power of terms and terms with higher derivatives. However, since we are interested in the physics near the critical temperature, and at the critical temperature the magnetization is small and the correlation lengths become infinite, then we can neglect higher order polynomial, because x to the 4th is much smaller than x squared divided by some characteristic length scale if x is small. That's what Taylor series is all about. And we're going to neglect higher order derivatives, because if correlation lengths go to infinity, that means that my fields will in general vary very slowly, because that means that if all spin density is correlated, then you have a field that maintains the same value for a very, very long time. the typical size of fluctuation of the magnetization field is precisely the correlation length. So in the presence of an infinite or a decoupled correlation length, very large compared to the typical scale of the problem, then of course derivatives of the fields will be small numbers, because that means that the field will change very slowly, right? So with this in mind, we have a recipe to neglect, for instance, coupling like phi to the fourth, or coupling like phi squared, phi squared. They would be subleading with respect to those we have included. So, in some sense, this is to say that this Landau Hamiltonian that was introduced phenomenologically by Landau may be motivated from a point of view of renormalization group theory arguments as well. Now, if you go back in the original textbooks or discussions by Landau and co-workers in many textbooks, you will discover that Landau formulated the theory not in terms of the Hamiltonian, but in terms of the Gibbs free energy as a function of magnetization directly. What we're going to do here instead is start from a Hamiltonian describing this local spin density and then arrive to the expression of the Gibbs free energy by using field theory and calculating the Legendre transform in field theory. So this will be the results of a calculation. So from the point of view, conceptual point of view, you can think about what we are doing here as being more microscopic than what is normally done in the textbook descriptions, most textbooks description of Landau theory. Now, on the other hand, the description you find here was mostly taken from the Bellak's book on quantum statistical field theory. So there you have an alternative derivation of whatever I'm going to say today in the next lectures, in a textbook form, and of course in my notes. Okay, so that's my Hamiltonian. And of course, I want to add to the Hamiltonian a coupling with an external source. So I will couple this to an external magnetic field. So I will do this plus integral d dx by of x phi of x. And I want to put a negative sign here to remind me that the interaction is attractive. Now, with this in mind, I can define a generating functional z of b, which is nothing but, okay, let me call this w to be consistent with my notes. And the source term, w will depend on b, and the source term, and then of course the Hamiltonian will be w of b minus the source term, so plus b phi. So in other words, this is the Hamiltonian up to here, the Hamiltonian plus the source term s given w. So with this in mind, my partition function can be written as z of b integral d phi e to the negative h of phi, I'm setting beta to 1 for simplicity, e to d plus integral dx d dimension b of x phi of x. The plus comes from the attractive interaction, the negative sign in the magnetic coupling between the spin density and the external magnetic field. So this looks very much like a phi to the 4 generating functional we've used so far. It is the same generating functional, with the only difference that in this case b is the external source that we normally define as j, and we call it b because it has a physical interpretation of a magnetic field. So unlike the perturbative case when the external source was just a mathematical artifact to condense all the evaluation of arbitrary correlation function into one object, the generating functional, here the external source is a physical object, and we might want to leave it finite if we want to, if my system is actually immersed in an external magnetic field with some particular space dependence. So we are interested in the most general case in which the source can be finite as well. Okay, so we have, let me rewrite it here as I begin new slice. We have a theory We have a partition function, and now I'm using the dot notation I used several times. We have a theory, we have a partition function, and we want to compute a generating functional. But really, if our goal is to understanding, for instance, the emergence of a phase transition from starting from this theory, what we really want is to understand the emergence of thermodynamic states with finite magnetization. So we define the magnetization field as the expectation value in this theory, which in general contains a finite magnetic field, not of the local spin density, phi. And this is our order parameter. And of course, if our system is homogeneous and the magnetic field is spatially homogeneous and translational invariant, this is going to be a constant, m. And we want to find out whether there are thermodynamically stable systems with finite m, which means that technically what we need to do is to go from the Helmholtz free energy, which is intrinsic in the definition of the partition function. The Helmholtz free energy is defined as f to the minus f of b equal to z of b, right? That's the Helmholtz free energy. We want to go to the Gibbs free energy, which I would call gamma of m, and stable states will be minima of the Gibbs free energy. And if there is a stable state with a finite m, then the system will be spontaneously magnetized, or will have a magnetized phase. In this case, this is a metastable, this is a stable state. Conversely, if the system has a single state when the magnetization is 0, then, and that's the Gibbs free energy, then the system will not contain any magnetic phase, and so this will be the paramagnetic phase. So in general, the ferromagnetic phase transition comes from having single-shaped gamma of m going at Tc, after below Tc, into a state in which I have multiple states, and I'd say maybe m and negative m below states. And they might not be degenerate if there's a magnetic field. Of course, only one is stable, and we can think about other things entering the game. But at the critical temperature, the zero magnetization phase becomes unstable, and you might roll off in either of these states where the system gets magnetized. So really, our object of interest is computing the free energy, the Gibbs free energy, because by looking at the structure of the Gibbs free energy, we can infer the existence of phase transitions. So the technical question we need to ask is, given the theory defined by Z of B, how can we compute gamma of m? That's our goal. That's what we want to compute, right? And that's the non-perturbative goal we're setting. Okay, now the crucial observation we want to start off with is that in the definition of Z of B, the fields which define the magnetization through their mean value and the source are linearly coupled. This linear coupling is the key to perform what is called a Legendre transformation. That's exactly what happens when you go from Lagrangian to Hamiltonian formulation, right? You perform a Legendre transformation of Lagrangian. This is a function of q dot and q into a formulation of p and q. In this case, q dot and p and q are conjugate variables. So, with this in mind, we define the Gibbs free energy as a Legendre transformation. So first thing we're going to note is what I just said, that the magnetization is defined as the mean value of phi with respect to x, and that's defined as the negative functional derivative with respect to b of the Helmholtz free energy. So this result should be at this level. This equality should be clear to you because it's the same equality we use to derive correlation function given a partition function from the external source. Remember, by functional differentiating with respect to the source of the logarithm of the functional, we were getting the negative of the expectation value of the field. So that's what we're using here, because this negative f is nothing but the logarithm of the generating function. So here, of course, is a function of x. And then the Legendre transformation is defined in the following way. This is given by f of b plus integral d dimensions m of x and b of x. But we want to evaluate this with the magnetic field substituted by its expressions in terms of magnetization. So that's what we do when we define Hamiltonian. We do q dot p minus L, but with the q dot as a function of p and q. Remember? Well, that's what we're doing here. We want to write this sum, but then we're not content with this sum. We want to replace the magnetic field with a magnetization. That means that we have to write the magnetic field as a magnetization, a function of magnetization, and the result will be a function of magnetization and not of the magnetic field. I might be repeating concepts some of you know, but the point that I want to sort of emphasize in this lecture is that computing gamma is far from trivial, because writing down the path integral that sits here is not computing. If I ask you, is this a magnetized phase or not? You cannot get an answer just by looking at an infinite dimensional integral, because you don't know the result of an infinite dimensional integral. And therefore, the fact that we were able to define this guy as in the first line of this board, and define the corresponding Gibbs free energy as in the last line of this board, doesn't mean we know anything about the system. We know to write down the equations of the system. We are in the same situation of writing down Newton's equations without being able to solve it, or writing down Maxwell's equation, but this doesn't necessarily grant us any understanding of some electric system, electrodynamical systems. We have to solve for the Maxwell's equation or solve for the integrals. So now Landau came across with a fantastic idea on how to solve the system. Well, since we want to replace, in the end of the calculation, the magnetic field with a magnetization, it's probably a good idea to write down an equation that relates the magnetic field to the magnetization, and that's clearly the following. Which is directly inferred from here, right? So this is the relationship that given a Gibbs free energy of magnetization will tell me what is the underlying magnetic field. Of course, this relationship holds a fixed temperature, as it should. So how do I compute gamma? So the brilliant idea I was referring to was to look at this integral and say, okay, let's try to solve it in saddle point approximation. Now, the big issue here is that this is an integral of an exponent. Now, if there exist configurations where the exponent is stationary, then I can go ahead and retain only the configurations in a very, very, very close functional vicinity of the extreme. We have encountered this argument already in the course when we were deriving classical mechanics starting from Feynman's path integral. We used the stationary phase approximation, right? Now here we use the saddle point approximation, which is the exact analog, but not in the presence of a complex phase, but in the presence of an exponentially decreasing function at the being integrated over. So if you want, the mathematical idea is most clearly understood if we do a one-dimensional example. Suppose we have a function z, is an integral of dx, and then I have an integral of a negative of a function f. Now what you basically do, you're saying, let me find out the point where the function is least. Let's call it x0. That's the point where the function x is least, which of course satisfies f double prime evaluated at x0 equal to 0. Well, if I can do that, then I can expand the function around x0, and the leading order term will vanish. And if this is a minimum point and not a maximum point, I will have a positive second order term, which means I will get a minus 1/2 f double prime x0, and then I will get x minus x0 squared. And this term here will be greater than 0. And of course I will get corrections, which means that this is equivalent to saying that the partition function in this one-dimensional system has an integral over distribution, and I'm approximating the distribution with the Gaussian at its minimum. I might make some errors here and here due to the fact that the function being integrated over is not exactly a Gaussian distribution. It's probably not completely Gaussian here and not completely Gaussian here. But these errors that I'm making here are concerned regions where the distribution is exponentially small. So if I'm lucky enough, they will bring in errors that are subleading. So that's the whole idea behind the saddle point approximation. And if I do that, then I can take out this term out of the integral, which will become f to the minus negative x0. So let me rename the integral dy, and then I will get f x0 y squared. So when my function, my partition function of a single particle is evaluated this way, I will get f0. This can go outside the integral. So we said fx0, and then there's this Gaussian integral that we just referred to. And once again, if you remember, if you are in a stable point, this is greater than 0, and so this is a well-defined Gaussian integral, can be evaluated, and this is proportional up to an overall constant to 1 over root of f second x0 plus a number, we don't care. Now, this will give something like e to the minus fx0 minus 1/2 log, and I guess it's plus 1/2 and negative 1/2 log of f double prime in x0. So the point to notice here is that the effect of fluctuations around the flux point comes as a logarithmic correction to this driving term. So in other words, if all we are interested in is the dependency of the partition function of this point, we can consider this as subleading. And therefore, to the lowest level of approximation, we can say the partition function is up to a constant or a logarithmically slowly varying function proportional to e to the minus f0. Sorry, I shut the door. including this term here, which accounts for fluctuations, is called the Ginzburg correction, or the lowest order fluctuation correction. And it represents a Gaussian, if you want, approximation around the stationary point. Of course, if your systems have more than one stationary point, then you want to sum over the contribution of all the stationary points, and this will become a sum over all the f-naught i's, and we're going to move this through. Okay, so that's the basic idea. And we begin by doing the Landau approximation, which is basically this. And then we will account for the Ginzburg correction. So let's consider first the Landau approximation. In our case, the partition function is a function of fields, which is nothing but an infinite dimensional generalization of what we just said. And we will call this exponent here W. So W is going to be H minus B big dot phi. So if we want to apply the stationary point, solid point approximation to this path integral, we need to find stationary points of the exponent. So we're going to perform the functional differentiation with respect to the fields at the point x of the W functional, which is a functional of the field, but also of the external source field, and set it equal to 0. That's the equivalent of doing f prime of x naught equal to 0 and solve for f naught, for x naught. So here we want to solve for the field. So this equation will lead to an equation in which I will first perform the functional differentiation of the Hamiltonian and set it equal to b of x. Now this is a functional equation. If you want, if you look at it, it's basically has the structure of a Schrödinger equation, because the Hamiltonian is quadratic in the field. So whenever you, well, it's more like to be more specific. This has the structure of a Hartree equation, as we shall see. Well, let's look at it. Let's look at it and see what it is. So let's elaborate on this question, on this equation. So to see what this equation is all about, let me remind you that the Hamiltonian, now I'm going to change the name of the integration here, because the field is defined at x. I don't want to use the same letter within the integral. So I get phi of x negative 1/2 plus r naught half plus u naught fourth phi of x squared phi of x. That's my Hamiltonian. Now, let me first concentrate on the quadratic term, which is this, and this. Now, it is clear that when I act with my functional derivative, when I act on this term, I have two choices. I can either act on here and on there, and that's why you have a factor 1/2 here to account for this term. It is slightly less clear when you do it on this, but if you, the first time you act on the left, and then you have the derivative, but when you want to act on the right, you can perform twice integration by part and transfer the derivative on the left. So in the end of the day, however you're going to put it, you're going to get the same result twice. And when you act here, you're going to get a factor phi to the cube. So the result of setting this equation will be something like negative Laplacian plus r naught phi of x plus 1/2 u naught phi cube of x equal b of x. So it's a non-linear differential, partial differential equation. And those of you who come from many-body theory background or from Beck, BC background, they will recognize the structure of a Gross-Pitagayevsky equation or a Hartree equation. That's a typical structure of all subtle point or mean field approximation you're going to do with bosonic fields. With fermionic fields, you get the same structure, but you get additional properties that come from the antisymmetry of the wave function, and we're not going to touch on that. Okay, so this is an equation, and you can imagine to be able to solve this equation. Now, we do not know what the solution is, but the real cool thing about the Landau theory is that you get information without having to explicitly solve this equation. So let's suppose we knew the solution of this equation, which we don't, but we pretend we do. So some solution exists, and let me call phi bar of b the solution of the saddle point equation. I call it bar to specify that it's one solution, and I call it suffix b to remember myself that it depends on what kind of external field I had, because that will generate a different equation, and anytime I have a different equation, I have a different solution, of course. Okay, so now we assume we have that. And once we have that, let me go make sure I'm using the correct notation in my notes, not to confuse you too much. Okay, so now I want to do the Legendre transformation. So to do the Legendre transformation, I have explicitly, well, let's do this. I say the Gibbs free energy as a function of magnetization. It's going to be remember, Helmholtz free energy as a function of field plus integral dy, there's a d in general, m of x, b of x, and let's call this x at this point, evaluated for b expressed in terms of m. Okay. Now, at this point, we use the Landau approximation, say that z of b is basically a constant, which we're going to immediately disregard, and it's e to the negative of the Hamiltonian evaluated in phi bar plus phi bar slash b, and this is of course an integral. But immediately, remember, what we want to do is to express things in terms of m only, so it's actually interesting to relate it. So this expression is expressed in terms of b through the phi bar, because the structure of the B field determines the structure of the solution phi bar. We want instead a solution in terms of the magnetization. So we want to relate phi bar to the magnetization. So understand what is this relationship. But in order to do that, let me remind you that the magnetization is the expectation value of the field, and the magnetization is therefore negative of the functional derivative with respect to the source of the logarithm of the partition function. We know this from our previous part of the course on correlation function. Remember, we did exactly the same, but replacing b with j. Go back in the notes when we relate the generating function out to correlation functions. Now, if you now use the saddle point expression for this, then you immediately discover that at the saddle point level, this becomes exactly 5. Now, what it's written here, it should not be surprising anyone. It's telling me that if you work at mean field level, the average value of the field is the most probable value of the field. Most probable, the one with a high statistical average, mean. So restricting to the most probable actually corresponds to make a mean field and considering only a mean value. And we have already encountered a situation like this when we derived classical mechanics from Feynman's path integral. We look at a path which had a stationary action, which was a smooth path, but we consider this as the mean of a many stochastic path which contributed to path integral around it. And the fact that we get a mean field from a stationary point or a saddle point approximation is is universal. So if you want, classical mechanics is mean field theory of quantum mechanics, and in this case we have a magnetization, which is the expectation value of the spin density, is actually the most probable saddle point field. Very well. With this in mind, now we can proceed and evaluate precisely gamma, because gamma, and I use a different color for some reason, it's negative log z plus integral mb, evaluated as a function of m. Now, negative log z is actually phi of phi bar, sorry, is the Hamiltonian written as a function, is the Hamiltonian written as a function of phi bar, but phi bar is the magnetization. So I have achieved the first goal, that is replacing at least the first term as a function of magnetization and not as a function of magnetic field. Then I have negative integral, and then I have b times phi bar, which again is the magnetization. So let me replace this with magnetization. And I have then the identical integral b dot phi bar that comes from here. So this term here comes from the saddle, these two terms come from the saddle point expression of this, and this term here comes from the Legendre transformation. Now, due to this cancellation, which is not a coincidence, is how the Legendre transformation is built on conjugate variables, which means that you get this cancellation. So this cancellation should not be surprising. It's just the fact that these are conjugate variables and you are supposed to be getting this cancellation. So that's what you get. So our result is really striking. It says that in order to get the Gibbs free energy at mean field level, all you need to do is to take your function of follow of the Hamiltonian and replace the fields with the magnetization, which is the expectation value of the fields. So basically you're getting the energy of the mean field. That's physically sensible, but we derived it in a formal manner. Now we're going to make additional assumption. Now we're going to say the system is uniform. If the system is uniform, then it's spatially invariant. So in particular, if the spatial system is spatially invariant, we don't expect to have any gradient of magnetization. Why should the magnetization be larger here than there if the system is translationally invariant? Okay, so this will lead to my Hamiltonian as a function of m, which is actually the Gibbs free energy, to be only given by R naught times m R naught m squared plus u naught m fourth. So let me write it this way, actually. So this looks like a parabola with a quartic component. However, remember, we are allowing the coefficients to round with temperature. Now here comes the brilliant phenomenological intuition of Landau. And I think what really made the Russian school superior in theoretical physics, to my eyes at least, but I think it's sort of a universal fact that the Russians had the best theoretical physicists in the USSR. I think what made their school so much superior to any other school in the world was the ability of combining strong mathematical skills, they were excellent mathematicians, but with great physics intuition. And with only one of the two, you make perhaps a good physicist or a good mathematician, but only when you combine both of them, you get a great theoretical physicist like Feynman, Landau. All these great people had something in common. They could see through things and get the right idea that really solves the missing beat of a physical explanation. And so what was Landau's great idea? And say, well, this potential here looks like this is locally quadratic and grows up like m to the fourth, unless R naught becomes negative. But R naught runs with temperature, right? So if there exists a Tc such that for a smaller temperature R naught is negative, then this shape here becomes this shape here. And all of a sudden, along with the stationary point here, m equals 0, which is now becoming unstable, so does not represent a physical state, two physical states emerge, which have opposite magnetization, m and negative m. That's really brilliant. So his idea was at Tc, R naught runs by changing sign. This is the definition of Tc. So already we have succeeded in explaining the emergence of a phase transition starting from Hamiltonian defining field theory that represented the local spin density by relying on the Landau approximation. Remember, we have now a theory that is formulated in terms of the magnetic field, the magnetization as a dynamical variable, as a thermodynamic coordinate rather than a dynamical variable. So one coordinate we did not explicitly touch, we hired in the definition of the units, was temperature. We set beta equal 1 for not having to carry around temperature, but now you can restore temperature in units, say in CDS units, and discover that temperature is always there, it's always been there from the beginning. And now we are defining two thermodynamic coordinates. One is temperature and the other one is magnetization. And we are discovering that as you hit a critical temperature Tc, then the physical state starts to have a finite magnetization, right? So in this diagram, though, the magnetic field does not appear. And you see, the magnetic field could be an external field or could be dynamically generated by the spins. But in none of these kind of options, there is any explicit reference to the magnetic field. But just as much as in the Helmholtz formulation, where you have explicit dependence of the magnetic field, you can get the magnetization as a calculation. Here you can get the magnetic field given the magnetization. And how you do that? Well, you remind yourself the equation that we wrote before, that the magnetic field is the conjugate to magnetization. So you have to write this thing. And you use your saddle point or Landau theory mean field approximation to gamma and discover that you get the results like that. So given the magnetization M3, you can get a field, or given the field, you can solve for the corresponding magnetization. This is a standard mean field theory. Now, an important comment. Landau theory is a rigorous low-energy, rigorous effective field theory of the Eisen model. We discussed this at the beginning of our excursion in statistical field theory. So we expect, by construction, that the low-energy observables calculated in the Eisen model should agree with the low-energy observables calculated in the effective field theory, provided you match the effective coefficients of the effective field theory to be consistent with the Eisen model. Now, for this reason, the low-energy observable, the magnetization, is a low-energy observable because it's static, stationary, it doesn't depend on momentum, so it's really is a vacuum property, if you want, a ground state property. It's a, there's no, is the lowest energy state you can think is one where the system is just constant, fixed magnetization. So it's really is an infrared observable. Well, in Landau theory, you obtain exactly the same mean field theory equations that you would have obtained starting from the Eisen model, by doing the famous mean field approximation of the Ising model. Those of you who have gone through the theory of ferromagnetic transition, they know that the Ising model is defined in this way. Sum over nearest neighbor, Si and Sj. And the mean field approximation is usually performed by changing the Hamiltonian, for instance, and replacing one of the spins with their mean value. And if you do that and you look for magnetization, you go ahead and you recover the same polynomial equation that we derived for small m. You get an arctange equation in general in mean field level, but remember Landau theory is only valid in the proximity of the phase transition, so you can expand in Taylor series that arctange and getting out a cubic polynomial, and the equation that you find is precisely the Landau theory result. Okay, so that completes our very superficial scratching of Landau theory, but our application of mean field theory is subtle point approximation. In the next lecture, we're going to make one step further and derive the Ginzburg corrections and ask ourselves what to do, how to go beyond mean field in a perturbative manner, which wouldn't correspond to doing completely perturbation theory because you are perturbing on a non-perturbative solution, which is the mean field. It's much different than perturbative on a completely trivial solution, like in the paramagnetic phase, where you perturb around zero magnetization. So depending on around which field configuration you do perturbation theory, your result will eventually be a non-perturbative or a perturbative result. This might sound confusing. I want to repeat it. When I do perturbation theory in the paramagnetic phase, I'm considering the field to be small, there is no magnetization, and I'm using the quadratic Hamiltonian as my unperturbed theory. That's perturbing around trivial free quadratic theory. That's what you normally call perturbation theory. When we do Ginzburg, we're going to perturb around the mean field. So we're going to write the field fluctuations are the mean field plus small fluctuations. Now, and we will play some kind of perturbation theory around these small fluctuations. However, these are small fluctuations around a point which is highly non-perturbative, and in this sense, Ginzburg theory provides a small correction to a non-perturbative result. So it's really non-perturbative results. Okay, that's it for today, and I'll see you soon.